So before we get started on the episode, I just wanted to say thank you to those that have been following me through this odyssey creating math content. A lot of you have come from Facebook and Reddit to check out what this stranger has to offer and have given me confidence to continue doing what I'm doing. There's not really many of you, but to those that are here watching this, you seem to appreciate the content. And that's kind of amazing. I just want to extend a special thanks to my friends for supporting this creative and academic endeavor. And to everyone watching, you really are the math homies. And I hope this channel can grow as we explore other branches of mathematics. On that note, I wanted to ask you guys what you'd like to see next. Now, I think I can do an all right job explaining real analysis or abstract algebra. So let me know in the comments down below what you want to see, and subscribe to the channel to see when those videos will be coming out. Anyways, here's the episode. So we meet again. This time we're going over the final boss that overwhelms every undergrad the first time they see it. Countability and infinity. String theorists like to mock it. Computer scientists pretend it doesn't exist. And statisticians are enslaved to it. You're no longer the hopeful undergrad, but you're a better student. You know how to visualize problems and rely on intuition instead of the way squiggles are supposed to move. You know how to exhaust cases, generalize properties, and even attempt in some Putnam problems. And you might be thinking about what kind of research you'll be doing, because learning to prove some basic theorems has given you enough confidence to solve the Riemann hypothesis. Slow down. We still have some questions to ask. What even is infinity, and how do we describe it? Well, I have bad news for you. There are different types of infinity, and they might surprise you if you're not careful. What? But infinity means infinity. What drugs have you been taking? All of them, but that's besides the point. For the purpose of this video, we will consider two types, a countable infinity and an uncountable infinity. Let's start with countable. Suppose we can find a function f from n to s such that f is a bijection. Then s is considered to be countable. We denote the cardinality of n, or the number of elements within the set, to be all if not. Notice n is countable because a bijection is formed when we choose n to be the identity function. Now I'll pose a question for you. Which set has a larger cardinality? Z, the set of integers, or n, the set of natural numbers? The answer is neither. They have the same number of elements. Remember, a set is countably infinite if there exists a bijection between n and the set. The question we must ask is, can we find a bijection between n and z? Intuitively, we may count z in an in and out sort of way. Start with 0, then count 1, then -1, then 2, then -2, and so on. Every input maps uniquely to an output, and every integer has an input in n. Analogously, we have found a sequence that hits every element of z exactly once. Not only that, but we can describe that sequence as the following function, which returns n over 2 when n is even, and -n plus 1 over 2 when n is odd. What does this mean? It means even when we effectively double the number of elements in a countably infinite set, the number of elements is still the same. It gets weirder. Let's look at Q. Q is the set of all fractions, or rational numbers. We have in-betweens for every integer. There's an infinite number of fractions between 0 and 1. There's an infinite number of fractions between 1 and 2. You'd have to be some sort of idiot to think that n and q have the same cardinality. No way. No how. Nope. Can't happen. Alright, fine. It looks like q is countable, but how? The answer comes from how q is constructed. Let's take a moment to just acknowledge q+, which can be represented as a set of ordered pairs from n cross n, meaning we could just list the elements of q+ as a table. If we construct a sequence on the diagonals of this matrix-like object, this shows a sequence that counts every element of q+, and hence q+ is countable. But if we learned anything from z, if we happen to throw 0 in q-, we could also show the entirety of q is countable. So n, z, and q all have the same cardinality. If you're not freaking out about this, you're probably a sociopath. Or at least a jaded undergrad in his or her second semester of analysis or abstract algebra, wondering why this is any bit in the least surprising. So a sociopath. Okay, maybe you're not that impressed, but I said there was two types of infinity we're going to consider, and we've only talked about countably infinite sets, and you're probably still not convinced that infinity isn't just infinity, and there's nothing else to it. Let's get real for a moment. R is the set of real numbers, and I'm claiming that the cardinality of R is a bigger infinity than the cardinality of n. That's right, bigger and better, because R is complete and allows for smooth calculus, but that's for a later lesson. So how do we go about proving that R is a bigger infinity? Well, we basically need to show there doesn't exist any bijection between n and R. We could just try every function on n that maps to R, but there's a problem. There's an indefinite number of functions that map n to R, so we can't just try them all. So what do? This is where our previous knowledge of logic comes in. We'll assume to the contrary that there exists a bijective mapping between n and R, and try to show that it yields a contradiction. Suppose a function exists, but instead of mapping to R, we'll say that it's just the interval from 0 to 1. It just makes the proof easier to visualize if we restrict the codomain to just an interval. Then the mapping will look like this. If we generalize this, 1 will map to some arbitrary decimal between 0 and 1, 2 will map to some other arbitrary decimal, and for any k, the same will be true. Each a is a digit between 0 and 9, inclusive, that represents the jth digit corresponding to the ith input. Since we're assuming this is a bijection, that means every number between 0 and 1 is being mapped to, uniquely, from one singular input in n. But we can in fact find a number that isn't being mapped to. If we look at each aii on the diagonal, we can create a new number, 0.b1, b2, b3, b4, b5, and so on, such that b1 is not a11, and b2 is not a22, etc. This new number does not belong to any input in n, so the interval between 0 and 1, including irrational numbers, is a greater infinity than n, which means R has established dominance over n, since it's not only definitively bigger, but also surrounds n with vast oceans of irrationality. We'll let the cardinality of R be a new symbol, which we'll call Aleph1. One question that was proposed was considering what it would mean to have an in-betweenity, or if you're not a kindergartner, an infinity between Aleph1 and Aleph0. The answer is, drumroll please, fuck all. We can't really say. We can't prove or disprove it with the Zermelo-Fraenkel axioms of set theory, so we're kind of free to assume it is or isn't true. But that's the high-level frou-frou knowledge mathematicians are famous for spouting. In a more concrete sense, if you can even call it that, we can continuously define higher orders of infinity by finding the power set of a particular set. The power set is the collection of all subsets of a set. So the power set of crying, sobbing, and anxiety is this. The power set for natural numbers is obviously not finite. However, we can prove the power set of n is definitively larger than n, and thus would have a cardinality greater than Aleph0. It is the statement of the continuum hypothesis that allows us to say that the cardinality of the power set of n is equivalent to the cardinality of R, or Aleph1. Now, we could also find the power set of power sets, but higher order infinities, cardinals, ordinals, and axiomatic set theory is its own course beyond the scope of a YouTube miniseries. Maybe you can find the answers through someone on the Math Memes subreddit. Now you get to show off to all your friends and talk about something mind-blowing that only a fraction of them will be interested in.
That's all right. You know the ultimate truth. Now spread the good word and keep spreading it until all of your friends and families hate you. Go above and beyond and preach on Pi Day, Tau Day, every day. March forward. Terminate every forum and subreddit with math memes. Control the memes. Control the world. We will become one. We will become the everlasting. We will become infinite in wisdom and power. We will rule with an iron fist. Math for everyone. Math for the ages. Math everywhere. It will burn down at the hands of math. Every last one of them will say. Every last one of them will say.
I think I'm gonna grab some water after that. Anyways, I hope you enjoyed this video and this video series. I do plan on making more, and I do have some plans for how to move forward. But if you could share this video with your friends and give a thumbs up, that'd be a big help. I appreciate everyone that stuck with me through this series, and I look forward to creating more. Thank you for your time, and keep learning.